In this module, we want to start talking about motion. And the first thing we want to do is figure out a way to quantify that motion. And to do that, we're going to learn about the trajectory. The trajectory is what we call the function that describes the motion quantitatively. So let's say I want to describe the motion of the following event, which is a water balloon thrown out of a second-story window. So how would I go about doing that? The first thing that I would do is draw a picture. So I have a second-story window. So that's up here somewhere. I have a person, and they toss this water balloon out of the window, and then it goes sploosh somewhere there on the ground. So if I try to think about that motion, and that's why a picture is so important, you can sort of visualize what is actually happening in the physical system. And now I want to think about the components that go into it. And it turns out to be pretty complicated. I can think about this water balloon. It's not a rigid object. It's sloshing around. There's air resistance. It has a weird shape, and there's all sorts of complications. And this is not unique to this system. I should tell you right from the beginning that no real system can be calculated exactly. Now, some people find this kind of disappointing, but that is the nature of our business. There simply doesn't exist any real physical system for which, from fundamental physical principles, we can come up with an exact answer. So that brings us to the next step of something that's very important for this class, which are models. Because we can't calculate the real system exactly, we have to develop a model that is going to simplify our system in such a way that we can come up with a quantitative description. So our quantitative description is going to be for our model, and we hope that the model represents the physical system to the best of our accuracy. So the question is, how simple should it be? And the answer is ASAP, as simple as possible. So as simple as possible, such that it still contains enough info. Enough information. Well, how much is enough? That's part of what we're going to be teaching in this course. You need a model simple enough that it contains the essential physics, but not any more to make it too complicated. So if that sounds vague, we're going to be talking about that more as the course goes along. But at this point, I want to introduce you to one particular model that we'll be using a lot, and we want to use it in this example here, which is the particle model. So the particle model is where we represent a complicated object like our water balloon as a point. And by a point, I mean it has no volume, and no structure. So I'm simplifying my problem. I'm going to completely ignore the complicated structure, the sloshing, everything else of my water balloon. I'm going to represent it as a single point. And so you can see how useful the particle model is, because at any point in in time, then, since my particle is a single point, I can represent it by a set of numbers or a vector or particular set of coordinates in space. So that's the first. After I have a picture, I establish a model, what sort of approximations I'm going to have, and now I want to begin to quantify this system. I'm going to draw a schematic. A schematic is different than my picture. My picture is something I use to be able to visualize in my head what's going on with the physical system. Now, a schematic is how I put that picture, or more exactly, the model of my picture, on a quantitative basis. So part of a schematic is my coordinate system. And part of a coordinate system, then, is to establish where my positive axes are. In this case, I'm going to have a positive x and y axis, and where my zero is, where my origin is of both of those axes. So now, if I were to say, I know that the water balloon started at 10 meters above the ground, and so I put 10 meters here as the start, and then if I look at the trajectory, then I see that it followed this path and then hit the ground. Okay, so now I no longer have to worry about the structure of the water balloon. I have this particle that's moving through space. And so I have a specific coordinate system, and also I have to establish not just where my origin of space is, but my origin of time, t is equal to 0. And here I say that the t equals 0, the time is when the particle is launched from the second story, which is here 10 meters above the ground. Okay, so from my schematic, I want to create a motion diagram, which is now the location of this particle at even intervals in time. So at t is equal to 0, then the particle is still right where it's going to leave. At t is equal to 1, it's at this point. 2 is this point. 3, then 4, and then hits the ground. And so these now represent snapshots, or the motion diagram of where this particle is in space. Now that I have a motion diagram, I can represent each of these points in space with a vector. So each of these points can be represented quantitatively with a vector. And now I'm just saying that I've been able to measure this accurately. This is 5 meters, 10, 15, 20, and 25. And let's say that I've been able to measure these points in space. And so, in doing so, I find that at t is equal to 0, the location represented by the first vector, which I'll call r sub 0, is at the position in our one form of our vector notation, 0 and 10 meters, or in our coordinate system notation, 0 I hat plus 10 meters j hat. So at t is equal to 1, that's this part here, that's represented by a vector r sub 1, which is x is equal to 5 meters, and y is equal to 15 meters. Or if I want to represent that in our other notation, 5 meters I hat plus 15 meters j hat. And so this is then R1. If this is R2, R3, and R4, I can measure what each of those are. R2 is that its x-coordinate is now 10. The y-coordinate, I'm going to say, is 16. And so that's 10 meters I hat plus 16 meters j hat. And the last two, R3, is equal to 15 and 13 meters. My numbers here may not exactly match my schematic because of my drawing skills, but we're, say, in the real life example, I can measure these numbers to this accuracy, and t is equal to 4, R4 is equal to 20 and 6 as it starts falling meters, or 20 meters I hat plus 6 meters j hat. So the important thing here is that once I have my schematic and my model, I can create a motion diagram of this particle moving through space at equal intervals of time. Once I do that, I can represent those particles in space once I have a coordinate system with my vectors. Now, these vectors represent points in time of a function, a vector function r of t. So if this function here is continuous in time, a continuous function of time, and this is called the trajectory. So the motion diagram represents snapshots of the trajectory, which is a continuous function of time, and it describes then the motion of this particle for every point in time. In fact, if I were to take these motion diagram values and fit it to a function, I could in fact find that the trajectory of this particular particle as a function of time is equal to 5t, where t is time, meters I hat, plus 10 plus 7t minus 2t squared meters j hat. Now, I'm not going to pretend that this is a realistic function for a water balloon. I put these numbers here just as an example. But this now, for this particular example, is the trajectory. It represents the vector at every point in time that represents where that particle is during this motion. And at each second, the motion diagram gives us snapshots of where that particle is. And it relies on a schematic, our coordinate system, and the particle model, which represents this water balloon as an individual particle moving through space. And so next, in the next module, we'll look at the displacement of this particle, or the differences in different points in the trajectory as the particle moves through space as well. And that's the end of this module.